talk about beyond the worst case analysis for graph partitioning problems, and particularly I will tell you about a new model we introduced together with Yuri Makarychev and Vijay Raghavan, which we call the pi model, and I will tell you how to get constant factor approximation for the problem. Let me start with some general motivation for the beyond the worst case analysis, and maybe more generally for combinatorial optimization. So combinatorial optimization is the area that so the combinatorial optimization is used widely in business, science, engineering, and examples of combinatorial optimization problems are various problems in logistics, most importantly the traveling salesperson problem, various problems like constraint satisfaction, and today I will tell you talk mostly about problems related to graph partitioning. And by the way, so I want this talk to be very interactive, especially since I don't know what your interests are. So feel free to interrupt me anytime you have questions. And so ask questions, and especially when I give some definitions. The history of combinatorial optimization goes back to 1940s, and there are many techniques today for solving problems like linear programming, semi-definite programming, more generally convex optimization. There are various techniques based on combinatorial methods. The most basic methods are like greedy algorithms, local search, dynamic programming. And today we know that some problems are NP-hard. So many combinatorial optimization problems, essentially all sort of famous combinatorial optimization problems are NP-hard, and we can solve them exactly. So, for example, the linear programming algorithm goes back to the work of Danzig in 1947. So, instead of solving problems exactly, what we try to do today is to solve problems approximately. So this is a notion of approximation algorithm that has been studied a lot. And suppose they have a maybe minimization problem where we want to find a solution to some problem and we want to minimize the cost. For example, maybe we want to find the shortest tour that goes that visits all vertices in our graph. This is a minimum travel salesperson problem. Then again, the problem is hard to solve, so we want to solve it. We want to find an algorithm that gives us a good approximation. Always gives us approximation of alpha. So we want the algorithm to return a solution that may not be the optimal, but at most alpha times optimal, where alpha is the approximation factor, and we want this alpha to be as close as 1 as possible. So if alpha is 1, then of course the solution returned by the algorithm can be always at least opt is optimal solution. So then the algorithm, the solution returned by the algorithm equals to ops, and that's the exact problem. Ideally, we want to get maybe some 1 plus epsilon approximation, but in real, for many problems, our approximation factors are much worse than 1 plus epsilon, as we may see today. So again, so for many problems, indeed, we can get what's called PITAs, polynomial time approximation schemes. That means that we can get 1 plus epsilon approximation. For some other problems, we may not get PITAs, and even we can get 1 plus epsilon approximation. In fact, today, there are techniques to show that the approximation factor of an algorithm can be good, can be small, unless p equals np, or under some other complexity assumptions. And so the question is, while we can't maybe solve the problem, some problem well in practice, can we do better in real life? Suppose the problem is hard to approximate. Can we solve the problem well? And for many problems, the answer is probably yes. So there are many heuristics that seem to work very well in practice, even for those problems that are sort of known to be extremely hard in theory. But now we can ask the same question, whether we can get some provable guarantees. Can we prove that there exists a good algorithm that doesn't work maybe in the worst case, but works very well in real life? And the question is not very well posed, so we don't really know what real life is. And so in this research beyond the worst case analysis that gets more and more popular today, we try to come up with some models of instances and show that in those models, algorithms can work well. In my opinion, there are two different ways of modeling real-life analysis. Instances, real-life problems. The first one is sort of based on structural properties. And the most basic example is to say that the graph is planar. Maybe if we care about logistics problems, if you want to find some shortest tour, then saying that our graph is planar is a good approximation to reality, because maybe our roadmap is planar. That's not exact model, but it's kind of close to a real-life model. There are other models like saying that our graphs have bounded tree width, maybe bounded genus, bounded degree. Recently, there were interesting works on stability. So works due to Balkan, Blum, Gupta, and then Bilolinial. And essentially, they argue that for many problems, especially problems arising in machine learning, there is a kind of interesting notion of stability, which roughly speaking says that suppose we take a problem and then slightly change the parameters. So what we want, the solution, the optimal solution, not to change when we slightly perturb maybe the weights on the edges. So think of an instance of your problem of some graph, weighted graphs, and suppose you slightly tweak your weights and you look how your solution changes. Your solution may, for example, be some partitioning of your graph into several pieces, satisfying some properties. So in practice, they say if a problem is interesting for machine learning, then the solution shouldn't change. Because if the instance is unstable, then somehow it's not very realistic that we find that problem is meaningful in real life, because it's not likely that when we try to solve the problem, we will find good the right set of parameters. So if we want to kind of use an unstable instance, then most likely when we set up our problem, we will make some small errors in the sort of weights, and in the end we get kind of a solution that doesn't make any sense anyway. So those problems may exist in practice, but we don't care about those anyway, because the solution we get from non-stable instances are not interesting. And there are many other structural models of real-life instances, but I won't talk about them today. Today I will talk about stochastic or generative models. And the oldest model is the planted cut model. So this is a name, it's sort of in theoretical computer science. And in other communities, this model is known as the stochastic block model. So this model is studied in theoretical computer science, in machine learning, statistics, and it's very popular in social sciences. So essentially, it says that the graph is Erdős-Renyi graph, and I will talk about this model just in a few moments. So I will postpone the definition, what exactly this model say. There are also various semi-random models where, so in the first model, kind of in the most basic model that people started looking into, essentially all decisions, sort of your graphs are kind of random, completely random, all decisions are independent. Then people started looking at kind of more complex models, sort of semi-random models, where we have some decisions made by kind of a random player, random decisions, and some sort of adversarial decisions. And I will give an example in a moment. So this is a kind of more complex model, and kind of a bit different angle at it is smooth analysis that was introduced by Spillman and Tang, and actually motivated by semi-random models. What they studied is the following question. Suppose we have a problem, and again, we slightly perturb coefficients, and we want to show that maybe our algorithm works fast. And they showed, for example, that the simplex method runs in polynomial time in this smooth model. So while we don't know whether the running time of simplex in the worst case is polynomial, if we slightly change the coefficient of our linear program, we know that simplex will run in polynomial time. And so what is the kind of purpose of beyond the worst case analysis? We want really to sort of understand what problems are easy in real life, and sort of what makes those problems, what kind of differentiates bad cases, hard cases of problems, and sort of easy cases. Today we'll talk about beyond the worst case analysis for graph partitioning problems. And specifically, so in general, in graph partitioning problems, we have a graph G, and we want to partition it into pieces. Typically, we want to minimize the number of cut edges. So the number of edges going from one piece to another, and we want to satisfy some properties. Today, we'll talk about the most basic model, which is the minimum balanced cut problem. But this is sort of the model problem, and most results that hold, like, that we can get for this problem, we can get essentially for maybe most or for many other graph partitioning problems. So what is this problem? We are given a graph G. It can be weighted or unweighted. That's not important. And we want to partition it in two pieces of roughly equal size, S and T, so as to minimize the number of cut edges. In other words, we want to partition it into pieces S and T. Both sets, S and T, should contain at least Cn vertices, where C is some number between 0 and half. Think of it maybe 25% of all vertices. So they can be slightly imbalanced, but generally they should be balanced. And we want to minimize the number of edges going from the left to the right part. Any questions about this problem? OK. So this is the problem we want to solve. So what is known about it? So this is the classical optimization problem. It's one of problems that Karp showed to be NP-hard. So we can't solve it exactly. There is a lot of research on approximation algorithms for this problem. So the first polylogarithmic approximation for this problem was given by Layton and Rao in 1989. So they gave an algorithm based on linear programming. Then their result was generalized for maybe different variants of the problem by Oman and Rabbani and Linger, London, and Rabinovich in '95. And a breakthrough sort of in 2004, Aurora, Rao, and Vazirani showed that there exists a square root log n approximation for this problem. So here n is the number of vertices. And so the algorithm of Aurora, Rao, and Vazirani is based on semi-definite programming. And the algorithm I will show today is also based on semi-definite programming, kind of similar relaxation for the problem. Let me know that if we care about partitioning the graph in exactly two equal pieces. So we want those pieces not to be approximately balanced, but be of exactly the same size. Then the best algorithm due to Reike gives log n approximation. And a natural question again, whether we can do better, whether we can get maybe a constant approximation instead of square root log n approximation. And we don't really know whether that's possible, but under some reasonable complexity assumptions, rather strong assumptions, but still reasonable, it's not possible. Also, there is evidence based on sort of integrality gaps for the relaxations used for the problem that suggests that maybe polylogarithmic approximation for the problem is the optimal. Maybe you can do better. Again, this is only some evidence that suggests that it's not possible. It's not known for certain. Okay. And so I will tell you whether we can do better in real life. And this question was posed in early 80s when Bew, Chudhuri-Layton, and Sipser, and then Dyer and Fries introduced the random planted cut model. And this model, again, is known in different communities as well as the stochastic block model. So let's generate our graph in a random way. So we start with two sets, L and R, on n vertices each. And then we add edges at random we add edges at random in L and in R with probability Q. So Q is some number. And we add edges at random between L and R with a different probability P. So in the end, the graph in the part L is a G and Q graph. So Erdős-Rényi graph with parameter Q. The graph in R is also a G and Q graph. And the graph between L and R is a bipartite GNN-P graph, right? So all the decisions are made completely independently for all edges. And this model has been extensively studied, and particularly due, for example, result to Bapana. If we know if Q is greater than P by a certain amount, here by square root of Q log n over n, then it turns out under these parameters, if we take this graph and give it to the algorithm, of course we will hide which vertices belong to L and R. The algorithm will be able to recover pieces L and R exactly with high probability. Of course, it's a probabilistic model, so with some small probability, but exponentially small, it won't be able to recover L and R. But with very high probability, it can recover L and R, and the cut between L and R will be the optimal minimum balanced cut. If so, this result is tight. Okay, so here I showed some other work on this problem, and this is a very small sample of all work. So every time I give this talk, I'll add several new names because all these results are very interesting. So a lot of known about this model. And as I said before, it is widely used. So many heuristics that are used in practice are shown to work well for this model. So it is kind of realistic. Again, social scientists use it a lot. But you may ask, why do we assume that the graphs in L and R are just random graphs? Is it realistic that they're GNP graphs? And many people kind of are unhappy with it because sort of maybe GNP graphs are not that common in real life, in practice. They're in a way too simple. So can we replace this model with something a little bit more general and kind of less restrictive? And in a work with Yuri and Arivindan in 2012, we suggested the following semi-random model. We start also with two sets, L and R. Both sets are on n vertices. And then we invite an adversary that sets arbitrary graphs in L and R. So the graphs L and R are completely adversarial. They can be just arbitrary graphs. And afterwards, we add edges between L and R with probability P. So we add every edge with probability P. So as in the previous model, the graph between L and R is GNN-P graph. So this is a graph we get. So the difference between the previous model, of course, is that L and R are adversarial graphs. Particularly, it's a generalization because the adversary may choose the graph sort of in L and in R to be GNQ graphs if he chooses to do so. In this model, as is, we can't hope to recover pieces L and R because the adversary may pick these sets L and R as he chooses, and particularly he can pick it as to be GNP graphs with the same parameter p as here. And then the whole graph is going to be a big GNP graph. And so there is no way that in that graph it will have 2n vertices. It's going to be G2np graph. There is no way, of course, in that graph we can recover the cut, the sort of displanted cut between L and R. But it turns out that we can find a constant factor approximation for this problem. So no matter what the graphs L and R are. And so why do we think that this sort of model is more realistic? More realistic than the previous model. Sort of think of that in the ideal world, maybe you have just two sets L and R, and you have some items. So all vertices maybe correspond to some items, objects, people that have some natural connections between each other, and those connections are quite complex. So we don't really know the nature of those links between vertices. So again, in the ideal world, we don't have any connections between L and R, maybe. So what we would get in the ideal world is just different connected components. So here 2, but you can generalize it to more than 2 components. Now, because of some noise, we have edges between L and R. And essentially, we want to get rid of that noise. So in this model, we really model only the noise by a GNP graph, but the real connections in L and R can be arbitrarily complex. And while we can't recover pieces L and R in general, assuming that L and R are sort of weak expander or satisfying some weak expanding properties, we can recover L and R up to little o 1 fraction of all vertices. So in a way, our result is similar to the previous result, but under much weaker conditions on the model. And so, okay, so this result, and you may not be quite happy with it because you may say, okay, it's nice that L and R are completely arbitrarily graphs, but what about sort of this noise between L and R? Why can't we assume that it's a GNP graph? Maybe your favorite distribution is some preferential attachment distribution. So what about that distribution? Or another kind of distribution that was studied in social sciences. Can we replace that graphs between the graph between L and R, the edges between L and R, with some other distribution? And it turns out that yes, we can do that. And this is the pi model I'm going to talk about. So the model is as follows. We have 2 adversaries. And first we invite the first adversary. Again, we start with the same 2 sets, L and R on n vertices. We invite the first adversary, and this adversary picks vertices in L and picks edges in L and R. So he chooses the graphs he chooses the edges in L and in R. Then we invite the second adversary to our room. But before doing that, we hide the graphs L and R. So what does it mean that we hide the graphs? So we hide the edges and permute vertices in L and R, randomly permute vertices. So the second adversary may know what the graphs were, because sort of the first and the second adversary could decide on the strategy in advance. But the second adversary doesn't know exactly the positions of the vertices. So sort of she sees the vertices, but doesn't know how exactly those graphs L and R are located. And she chooses the graph between L and R. So this graph, we combine the graphs, and we get this graph. So this is a model. Maybe let me state this model once again in a little bit different language, maybe a little bit more formally. So essentially, the first adversary picks some graph, L and R. So this graph can consist of 2 connected components, L and R. And the second adversary picks another graph, the graph H, which is a bipartite graph. So then we map randomly vertices from L to the left part of H to the left part of G, and from the right part of H to the right part of G. We pick this pi randomly. And this is a graph we get. So this is the graph we get in this model. So again, this is a generalization of the previous model, because the second adversary may pick a GNP graph at the second step, right? So this bipartite can be GNP graph. Again, we can't recover pieces L and R exactly or even approximately in this model. So this model is more general than the previous one. So what is the motivation for this model? Why we believe that it's kind of more realistic? The reason is that many maybe social communities can be so sort of the connections within social communities can be formed by kind of in some sense independent processes. So I live now in Seattle, and maybe most of my friends also live in Seattle, and so there are some kind of sort of social forces that create connections, my connections in Seattle. And I also have friends in Moscow, and I also have maybe some friends who are my colleagues, other computer scientists, but those processes are kind of almost independent. So I attend some conferences, I meet people, I create some social connections. I also visit Moscow, I have some friends here, and all these edges are in a way independent. They're not completely independent. It's possible that I know somebody in Seattle who is also Russian, and somehow because of that I know I have a friend in Moscow, and sort of who is a friend of that person, right? But by and large, we can assume that these forces are sort of independent, and this is the model we study. Let me give maybe the third definition. And this one explains why we call the model pi model. So pi stands for permutation-invariant random edges. So essentially, we can assume that we have two graphs, L and R, again, on n vertices, and in between we sample edges from a permutation-invariant distribution. So what is a permutation-invariant distribution? It's a distribution that's invariant over, under permuting vertices in L and in R. So note that this distribution doesn't have to be a GNP distribution. So as is, for example, the support of this distribution can only be various cycles, maybe it can be cycles, it can be matchings. So edges in that distribution don't have to be at all independent. That distribution can be a GNP distribution, which maybe is not an interesting case because other models cover that case. The distribution can be a preferential attachment distribution. Essentially any other studied distributions. So this is a model. And so what is our result? We sort of get a constant factor in quotes approximation algorithm. So there is some fine print to this. So we need to compare, in this case, the cost of the solution returned by the algorithm, so the number of cut edges, with the cost of the planted cut. So essentially the number of edges between L and R. So in this model, this planted cut doesn't have to be the optimal solution. So it's possible that there is a much cheaper cut in general. And in this case, we don't get a true constant factor approximation. I believe, so it's not like we can't show that we get a true constant factor approximation. I personally believe that probably we do get, but it requires a more complex proof. And we also have some additive term n log, n polylog n. And so essentially our result is interesting if the average degree in the graph between L and R is polylogarithmic. Otherwise, the result is correct, but it's just not interesting because you can apply some other known approximation algorithm and get this approximation or even a better approximation. Okay, and probably this is a good time to pause and ask you if you have any questions. And most importantly, whether you understood the definition of the model, or if you have any questions, I'd be happy to clarify.
I'm sorry,
yeah.
Does permutation invariance imply uniformity?
Uniformity of
distribution. No, if we have a permutation invariant distribution, does it mean that it's uniform on the probability of edges?
So
because you can actually as far as the model goes, your distribution describes the probability of an edge between two vertices. Yeah, right. And if you switch, like you can pick any permutation that keeps L and R sets intact, as sets, I mean. And then it actually implies that probability of any edge within L set or within R set is the same. And the probability of any edge crossing the cut is also the same. But they're not necessarily equal between each groups, I mean, group I mentioned, but within each group, like probabilities.
Yeah, so
would it be correct to say that marginal probabilities for the distribution for a single edge is uniform, but distribution for the ensemble of edges between the two groups? I mean, they're not necessarily independent, these edges, and therefore the distribution may be more complex than just a distribution.
For example, if you just take a random matching, it's invariant, but it's not uniform.
Okay.
So it's like the difference between exchangeability and independence.
right, yeah. So again, for all edges, the probability that edge is present as is the same. So the marginal probability. But if you look, as a kind of collection of edges, then you won't get independence, right? So kind of essentially because you can, if you kind of rename vertices, you have n vertices here, n vertices here. Now, if you rename all those vertices, you get the same distribution. And essentially, that's sort of essentially the definition. So it's sort of, in a way, what this property says is that sort of vertices don't have identities right? Or in other ways, maybe that this distribution doesn't see how exactly the graphs L and R are positioned. So it can depend. So for example, if you take the preferential attachment distribution, we can kind of define, so here are n vertices, here are n vertices, which generate this preferential attachment. What's important to note, and let me mention it, is that of course that preferential attachment distribution shouldn't depend on the graphs L and R that already sort of planted here and here. Does it answer your question? Yeah, but by the way, sorry, also feel free to I think, ask questions in Russian. So while I'm giving the talk in English, I'd be happy to clarify things in Russian as well. So it's important that you understand what's going on here.
Good. And do your result hold for any weights on edges?
Yes, I believe so. I think so, right? I think so. Yeah. I may need to double check, but I'm pretty sure yes. Yeah, the fine print, I mean, this part, actually, maybe you should be a little careful with the additive theorem then. Right, so it is stated as for unweighted graphs, but I believe that essentially the same result holds for weighted graphs, but you may be a little bit careful with this sort of additive theorem. More questions? Okay, so now we'll tell you about the algorithm, at least some ideas behind the algorithm. And so the algorithm uses semi-definite programming. This is a very powerful technique that's used for many graph partitioning problems. So what is it? It is similar to linear programming. And OK, this slide I wanted to draw something, but because I use a different laptop, I can't do that. So the idea is that for every vertex, we introduce a variable. So in the linear programming world, that variable would typically take values 0, 1, sort of actually a value between 0 and 1. And it would correspond to some probability. So in this case, maybe that would be a probability that that vertex belongs to the left part or the right part. And sort of, again, in the integral world, sort of in the best case, the solution to a linear program is integral. So essentially, all values are either 0 or 1s, and sort of 0 means that the vertex belongs to the left part, right part. Otherwise, if the value is somewhere in between 0 and 1, we get somehow a probability that the vertex belongs to the left part or right part. So to get some meaningful approximation for graph partitioning problems or for this minimum balance cut problem, you actually need to look at more complex relaxations where you have some distances between vertices. That's what Layton and Rao suggested in '89. But we will use not linear programming, but semi-definite programming. So in semi-definite programming, we also assign a variable to every vertex. But that variable is not a value and not a real value, but rather a vector in a high-dimensional space. So you can think of that space to have very high dimension. So of course, if you have 2n vectors, you can always assume that the dimension is at most 2n. So what we hope to get is this integral solution for our problem. So what we hope is that all vertices in the left part will be assigned some -1 vector, and all vertices in the right part will be assigned this -1 vector, and all vertices in the left part will be assigned sort of +1 vector. So it's kind of one-dimensional vectors. Or you can fix just some vector, call it v. So all vertices here will have this vector v assigned, and all vertices there will have this -v vector assigned. And then if you get a solution like that, you are happy because it's easy to get it, to retrieve the optimal solution. So in fact, of course, you'll get something else, but let me write what the optimization problem you want to optimize. So this is the SDP relaxation. Again, for every vector u, for every vertex u, we have a vector u bar. We require that all the vectors are unit vectors. And so let's see what our objective is. So objective is minimize the sum of square distances between u bar and v bar for those u's and v's that are connected with an edge. And we divide everything by 4. So if we get an integral solution like I showed in the previous slide, then in this sum, if two vertices u and v belong to the same part, they are both plus or minus 1, and u minus v bar is equal to 0. Again, squared, it's also 0. So the contribution to this term is equal to 0. If u and v belong to different parts, then the difference u bar minus v bar is either +2 or -2, and squared is 4, and when we divide it by 4, we get 1. So for every cut edges in that integral solution, this objective function pays 1. So if we write constraint only this constraint in our program, then the solution we get will be trivial. Anybody sees what solution we'll get? Suppose we write the constraint that we want to minimize this objective, and all vectors are unit vectors. Yeah, right, very good. Then we'll get just all vectors to be equal. And the objective is going to be 0. And that's kind of obvious, right? It corresponds to the problem of finding minimum cut. If you want just to find minimum cut, we'll just put all vertices on one side. So we need to add a spreading constraint that really says that the average distance between u and v is greater than something. So we normalize it, so its average is greater than 1 under this normalization. So you can verify, right, that it's in the optimal solution, in the optimal solution, we always have n vertices here and n vertices here. So distances in one part are 0, across a part are equal to 1 if we properly normalize them. What's important here is that we sum up over all pairs UV, not only over edges. And so this is a spreading constraint that kind of forces vectors to be spread sort of on the sphere. We will need some technical constraints, but those constraints are not particularly important. Those are called L2 squared triangle inequalities. So I will skip that part. And as I said, what we hope to get is a solution like this. But probably once we solve the relaxation, we get a different set of vectors. Essentially, all vectors will look kind of in different directions. And it's a kind of instructive to think of two extreme cases that we can get. The first one is an integral case, like that. And the first sort of when all vectors are almost random, looking at very different directions. Of course, we can get also some sort of mixture of two extreme cases. So what do we do? Here is a very high-level approach to, to solving the problem. We will use something called edge specification. So we'll take our instance, and the algorithm at the first phase will start removing some edges. So it will remove some edges between L and R, and maybe some other edges. And what we hope that at this phase, it will remove most edges between L and R, while not removing too many edges in general, so sort of in total. So after we remove most edges between L and R, the cut between L and R is sparse, and we use some off-the-shelf algorithm. For example, the algorithm of Aurora, Rao, and Vizirani, or Leighton and Rao, and find a cut using that algorithm between L and R. That cut may not be the planted cut between L and R, but it will be square root log n approximation to the optimal cut, or maybe log n approximation to the optimal cut, but after we removed edges between L and R. So at this point of time, the cut between L and R is very sparse. So the cost of this cut is going to be small. So once we kind of remember that we have edges between L and R that we removed, we can say that the cost of the cut we find is bounded by the sum of the number of edges removed by this specification procedure times the number of edges cut by this off-the-shelf algorithm. Of course, kind of this approach is a bit mysterious because we don't really know which edges to remove. If we knew what edges to remove between L and R, we would just remove all of them and find two pieces in L and R. So how do we do it? And remember, of course, that the algorithm doesn't know what the sets L and R are. So let's see. We will use some hint to guide us. Essentially, we somehow expect that edges between L and R are going to be longer than edges within L and within R. That's certainly true for the kind of intended solution, the solution we want to get where we had +1 and -1 vectors. It is to a certain extent true for that random solution, because sort of if we pick two random vectors in a high-dimensional space, two random unit vectors, then essentially they're going to be almost orthogonal, and the distance between these two vectors normalized like that is going to be half. But it's not clear why this is true, and that's kind of what we really need to show. So here is the algorithm we use. We solve the SDP. Then we fix some delta. So think of delta of being maybe something 0.1, 1 over 10, right? That's the delta, fixed length. And we find and remove all edges of length greater than delta. Then we, and again, this is just using that idea I told you about.
by edge length, you mean the distance between the corresponding vectors of two.
Right. In fact, to be more precise, it's square distance. It's square distance, so it's exactly the same quantity we had in the objective function of a semi-definite program. Okay, yeah, one thing actually I kind of forgot to mention, but which might be important, that we can solve semi-definite programs in polynomial time. That's well known. It's not so easy to see, but it's just known.
But will you provide us with details of a semi-definite program? Because you're talking about it, but you never listed it.
No, here is the, let me show it. Yeah, I showed it, but essentially we have three constraints, three main constraints, and some other constraints that are not particularly important. Essentially, what are these? This is a objective function. This is a spreading constraint. One other constraint which is important, that all vectors are unit vectors. So the length of vectors. Okay, this is sort of a semi-definite program in the vector form. You can kind of formulate semi-definite programs either sort of in this matrix form, saying, okay, here is a positive semi-definite matrix, and we want to minimize something. And in sort of combinatorial optimization, this form is more widely used. And so what's the relation between these two? So that positive semi-definite matrix is the gram matrix of these vectors. So ijth entry of that matrix is a dot product or inner product of sort of the corresponding vector, sort of ith vector and jth vector here. And it turns out that this can be written in the matrix form, and this is kind of more common actually form that's used in combinatorial optimizations. Again, we have some technical constraints that those are not particularly important. I'll skip that part.
Right, that in spectral clustering you use just trivial vectors of dimension 1 instead, right?
Right.
And as for spreading constraint, it is something different in this case, so I can't easily recognize.
So spectral techniques are different, right? So HDP is more powerful than spectral techniques. So HDPs are harder to solve. So there are much faster solvers that solve. But so this result sort of is not known. We thought a little bit. We don't know how to sort of replicate this result using sort of pure spectral methods. So some people also call semi-definite programming spectral, but if you think sort of about pure spectral methods, it's not so easy.
Okay, and maybe one more comment. What is the dimensionality of the vector u in this case? Is it a parameter or?
Yeah, the dimensions are what we would want to have. We would want to get these vectors in a low dimensional space. But that's not possible, really. I mean, we can assume that the dimension is log n, but that's again not very interesting, because in fact we don't get these vectors. When we solve the HDP, we get the matrix, the gram matrix, the matrix of inner products between vectors. So that's what we get. We somehow don't even know what the dimension we get. So then we can get we do something like Cholesky decomposition and retrieve the vectors. In practice, if you want to implement this algorithm, you don't want to get vectors at all. So it's enough to know the inner products, because from that you can retrieve all the information you need for the algorithm. So yeah, in fact, sort of it's just easier to think about the algorithm in terms of these vectors, but in practice you will never actually have these vectors sort of constructed by the algorithm. You will just get that positive semi-definite matrix produced by your solver. Yep.
Did I get correctly that in first place I must compute the length of each edge in graph, or are there some techniques?
What are these lengths of edges? These are really u bar minus v bar squared. So, okay, at the first step, sort of you solve this HDP relaxation, right? You take the graph. So how does this HDP relaxation depend on the graph, by the way? So the spreading constraint doesn't depend on the graph, pretty much. This one depends on the edges, right? Here is where we use edges of the graph. So the objective function depends on the graph. You solve the the relaxation, and then yes, you will need distances. Essentially, this u bar minus v bar squared in the algorithm. But that's that's. Is it? So as is, you will need to compute that. Any questions about the SDP relaxation? Any more questions? Okay, so here's again the algorithm. We solve that SDP relaxation. One other thing, of course, to know that the cost of the SDP relaxation is always less than the optimal cost. Because if you have an optimal solution, we can easily get sort of that intended solution where we have plus minus one vector, right? And the cost of that intended solution sort of is going to be exactly equal to the optimal solution. That's just one possible solution which we would want to get, but there could be a better SDP solution because it's a relaxation. So once we solve the SDP, again we remove all edges of length and delta, where length is according to the SDP relaxation. And then we find heavy balls of radius 3 delta. What are these balls? So we find really maybe the heaviest ball of radius 3 delta. We look in our space, and we look at balls around vertices of radius 3 delta and count the number of vertices in those balls, and just find the ball that contains most vertices. And we remove that ball. Essentially, we remove all vertices from the graph and all edges incident on those vertices. So we change the graph. And after that, we do something. Okay, yeah, so do something like this. We repair the graph. So I won't talk about the step. But the idea is that once we remove some edges from the graph and remove some sort of balls from the graph is no longer a graph from that pi model. It can be very different. It kind of doesn't satisfy some properties we hope. So we need to do something to the graph, kind of repair it. And this is a rather technical step. It's an important step. But again, I won't tell you. But it turns out it's kind of possible to repair it so that it again looks like a graph from that pi model. And then we repeat everything. What's important, we resolve the SDP again. So we resolve the SDP again. We get a new solution. We remove edges of length delta. We remove the heaviest ball. Again, repair the graph and continue. And we repeat till the sparsity of the cut or the value of the SDP solution drops by a factor maybe log n. Then we stop. It turns out that we will need maybe log n steps. So the number of steps of iterations of this algorithm is not that much. It's not that expensive to repeat this procedure many times. What's really expensive actually to solve the SDP even once. And what is the idea? Why does this algorithm work? It turns out that the number of remaining edges in the planted cut, so the number of edges between L and R, decreases exponentially, or decreases really fast after every iteration of the algorithm. That the reason why we need to resolve the SDP at this first step is because the cost of the SDP solution is upper bounded by the number of edges between L and R, right? So after we resolve this SDP, of course, for the remaining graph, and the cost of the optimal solution in the remaining graph is bounded by the number of edges that remain between L and R, which decreases exponentially. That's not obvious at all why it decreases exponentially, so I'll tell you in a moment. But the cost of the optimal solution decreases, and it means that the SDP value decreases very fast. Okay. This property holds true only for graphs from this pi model. So in general, that won't be true. For worst case graphs, that's not true. So for the sort of, I want to show, by the way, how much time do I have?
Definitely 25 minutes, even with our late start of 25 minutes.
Okay. Good. So I want to show you some maybe intuition behind the proof. I won't be able to tell you kind of all the details, and that's why I want to focus on the very special case, even though the result holds a general case. Suppose that the graph G, so sort of the graphs in L and R, right? So that was the graph G in our model. So sort of the internal graphs like in L and R are regular, and that degree is capital D. And the bipartite graph between L and R is also a regular graph of degree small d. And furthermore, let's assume that capital D is much greater than small d. This simplifies the problem a lot. So this is a much simpler problem, in fact. But anyway, I'll tell you why the algorithm works in this case. I'll at least give maybe some intuition. And sort of the main theorem that we show for this case is as follows. We call it geometric expansion. That suppose that after iteration t, the heaviest ball of radius 3 delta contains at most ETTN vertices. So ETT, right? Right. Okay, and then the size, or the number of, so denote by cut sub t the number of short edges, so edges of length at most delta between L and R. So this really cut sub t is the number of edges that remain between L and R in this bipartite graph between L and R after iteration t. That's cut t. And what we show is that the heaviest ball of radius 3 delta contains ETTN vertices, at most ETTN vertices, then the size of the cut is at most some constant ETT cut 0, where cut 0 is sort of the original size of the cut. So that's the size of the planted cut. And I may tell you a little bit about the proof, depending on how it goes. But the corollary of this theorem is that the cost of the SDP solution after iteration t is upper bounded by the cost of the optimal solution after iteration t, which in turn is upper bounded by this cut t, right? The number of edges between L and R, and this is bounded by ETT cut 0, the original cut. So let's use this theorem to get some results. Sorry. Okay, yeah. Okay, we will only analyze the second and the third step. So why do we remove, sort of, we need to bound the number of edges removed by our algorithm. And then we need to show that in the end of this algorithm, the sparsity, sort of, the cut between L and R is sparse. So how many edges can be removed at steps 2 of our algorithm over all iterations? So whenever we remove an edge of length delta, we decrease the cost of the SDP solution by delta, right? Just because the cost of the SDP solution is sum over all edges, the length of all edges. Okay, there was also a normalization factor of 4. So, but when we remove an edge, we decrease the value of delta. So for every edge removed, we decrease the SDP by delta. What's important, of course, that at the first step, we resolve the SDP. So that can change the value. But since the SDP solution of the previous step is also a feasible solution for this step, when we resolve the SDP value can only decrease even further. So essentially, the number of edges removed in total at all steps 2 is bounded by 1 over delta of the original SDP solution, which is bounded by 1 over delta of the optimum solution. And delta is some constant, maybe 1 over 10, so we get kind of 10 approximation for this step. Now, and note that here we don't really use any properties of the SPI model, so that would be true even for the worst case graphs. So now what happens for the third step? So at step 3, we remove some ball of size ETT n. And by the structural theorem, which I didn't prove to you, the number of cut edges, the cost of the SDP solution is bounded by ETT times cut 0. Now, how many edges do we cut when we remove this ball of radius 3 delta? And this is something known in approximation algorithm, that if we remove that ball, maybe in a little bit clever way, so we need to look at the small neighborhood of that ball, then we will cut at most 1 over delta times the SDP solution number of edges. So to do so, we need actually to look for maybe ball of radius not 3 delta, but for some radius, optimal radius between 3 delta and 4 delta. And if we look for the optimal radius, then we will cut at most SDP over delta number of edges. So the number of cut edges is bounded by C, some constant over delta, times this ETT cut 0. Now we can sort of charge every vertex removed at this step. We removed ETT and vertices, and we kind of paid ETT cut 0 edges times some constant. So we can charge every vertex with the cost cut 0 over n. Since in the algorithm we don't remove more than n vertices, that's well, maybe 2n vertices, that's how many vertices we have, the total number of edges removed at all steps number 3 is bounded by some constant times cut 0. Okay? Right? Here it's important that we remove many vertices at every step. So the number of vertices removed is sort of proportional to the number of edges cut at this step. And sort of this ratio remains even in the end. So questions? Yep.
Could you please explain why optimal solution is larger than SDP? Why SDP is smaller than the optimal solution?
Right, good. Because sort of the optimal solution, we can only, if we have an optimal solution, sort of pick an the optimal solution, then we can always define a SDP solution that just puts +1, right, to one side and -1 to vertices on the other side.
But there is some additional constraints on the SDP. But it would be
Good, right. So those constraints, okay, initially those constraints are satisfied. So that essentially we have an extra one constraint, the spreading constraint, right? So the spreading constraint is satisfied because in the optimal solution we have n vertices here and n vertices here. And so the average distance between vertices, depending on how we normalize the distance, is half, right? So essentially this probability half to random vertices are split, and this probability half, they're in the same part. So what I'm kind of hiding is, of course, after we change the graph, the optimal solution, so the restriction of the optimal solution to the remaining graph may not necessarily satisfy the SDP. So we should be a little bit careful with those constraints, but that's not a big, that's really a cosmetic issue. So it's easy to slightly change the SDP so that the optimal solution is still kind of a feasible SDP solution. Good. Right, so let me maybe, let me go back. So what did we achieve? We showed that sort of at steps number 2 and 3, we don't pay, or altogether, we don't pay too much. So the number of edges removed at those 2 steps is bounded by some constant, the number of of the planted cut. So in the end, of course, if the structural result is true, then the cost of the cut between L and R will become small just because we can't remove too many vertices at every step, right? So if we remove many vertices for long, then essentially we will partition our graph into just very small components. And sort of ETT will eventually become 0. Either it will become small or it will become 0. So the reason why we sparsify sort of our graph up to level 1 over log n, not lower, just because this theorem won't be true for very small values of ETT. And so in the end, we use that algorithm of maybe Aurora around Vizirani. For the remaining graph, we also have a bunch of small components that we kind of put back in the graph and kind of balance between L and R. The spreading constraint guarantees that those pieces we removed, so we remove pieces of radius roughly 3 delta or maybe 4 delta, are not very large. So that follows from the spreading constraint on the SDP, that those won't be too large. Because what could happen potentially that we remove one of those balls and that ball contain maybe all vertices. And that's not interesting, right? We just remove the whole graph. But the spreading constraint tells us that those pieces are small. And okay, I have some time, right? So let me show you maybe some ideas behind the proof of the structural theorem. For the proof, let's recall once again what was the pi model. So we had 2 graphs, G and H, chosen by the first and second adversary, and we had the random mapping pi. And what we want to show is that if G is D regular graph, so this graph is capital D regular, and this graph is small d regular, then the following claim again holds that if every ball of radius 3 delta contains at most eta n vertices, then the number of short edges in H, in this graph, right, in H, is at most the original number of edges in that graph times eta and times some constant. So suppose that that's false. Suppose that for our SDP solution, we have a violation. Then sort of this inequality is violated. Then the proof works as follows. We show that the Kolmogorov complexity of this permutation pi is very small. It's actually sort of prefix Kolmogorov complexity and conditioned on the graph itself. That it is much less than the entropy of the permutation pi. And this implies that the probability of such event is small. Or in other words, we show that there is just a small encoding of that permutation pi. Okay, how do we do this? The first step, we need to somehow encode the SDP solution. And in general, it may look kind of hard because the SDP solution consists of vectors in high-dimensional space, so the number of SDP solution is infinite. But it turns out that we don't need to store all distance. So what we care really about distances between vectors, not vectors themselves. And moreover, we care about approximate distances. So we don't care about exact distances. And the first idea we use is we embed our SDP solution in a low-dimensional space. So we project it using Johnson-Linier-Strauss transform to low-dimensional space, and then discretize it, so round all vectors to some epsilon net. It turns out if we do this, even if we pick the dimension to be very small, and if we pick the net to be very coarse, then the number of bits to store the SDP solution is much bigger than the number, not much, but it's bigger than the number of bits of entropy to store pi. So there is no way we can come up with a short description of pi using this. And the main idea we use, sort of one of the main ideas, is that we sample vertices in G and H. And so we sample every vertex in the graph G with probability 1 over capital D. And we sample every vertex in H with probability over small d. And then we store distances only between those sampled vertices. And it turns out if we carefully choose the dimension and sort of the epsilon net, then we won't use too many bits to store the SDP solution. So that's the first step. Okay, and now we need to somehow store pi. Okay, the idea is as follows. So pick a vertex x in the graph H, and we want to store where x is mapped. So the degree of x is small d. So with a constant probability, we sample one vertex from its neighborhood. Call it x prime. So for u, again, the degree of u is capital D, and with a constant probability, we sampled one vertex u prime from its neighborhood, right? So what we want to store is this mapping from x to x prime, and from x prime to u prime, and then from u prime to u prime. We can even assume that there is a unique vertex in the neighborhood of x. Let's assume for a second, with constant probability, there is a unique vertex x prime sampled in the neighborhood of x. Now, how many vertices sorry, the distance between x and u is just 0 in the SDP solution, because that's the same vertex, right? We assume that pi maps x to u. So now x prime is a neighborhood of x, and u prime is, sorry, x prime x is an edge in H, and u prime is an edge in G. So let's assume for a second that these two edges are short, that their lengths at most delta. That would imply that the distance between x prime and u prime is at most delta. Again, we assume that there is a unique vertex sampled in the neighborhood of x. There is a unique vertex sampled in the neighborhood of u, which happens with a constant probability. And then we assume that this edges x prime and u prime are of length at most delta. And we don't know what's the probability of this event so far. But if this happens, then the distance between x prime and u prime is at most 2 delta. And then we are kind of in a good shape, because we know that in the ball around x prime of radius 3 delta contains at most eta n vertices in our solution, in our SDP solution. That was the assumption. We assume that every ball of radius 3 delta contains at most eta n vertices. Now, the number of vertices sampled in the graph G is eta n over d, right? Because we sample every vertex with probability 1 over d. So this number, eta n over d, is the number of vertices, sampled vertices in the graph G, a distance at most 3 delta from x prime. And so to encode the index of u prime, to encode u prime for x prime, we need logarithm of eta n over d bits. Once we encoded this vertex u prime, we need to point to the vertex u. So we assumed under the simplification that the average, that the degree of every vertex in G is capital D. So we need another log D bits to pick the right neighbor of u prime. So in total, we have log eta n bits to store this mapping from x to u. But that's under two assumptions. First, that there is a unique x prime in the neighborhood of x. And second, essentially, that xx prime and uu prime are short edges, edges of length at most delta. Okay, it's why that edge uu prime is short. It's hard to say. So under this simplification, the graph G has much more edges than the graph H. And so somehow, if edges of the graph G were long, then they would contribute a lot to the SDP. And there is a way to show that sort of most edges somehow are short. So that happens with very high probability. Again, I don't want to go into technical details. And actually, if you want to have a formal proof, it's not so easy. But it turns out that because sort of G has many edges, most of them must be short. And we can assume essentially that all of them are short. Now the question is, what's the probability that x prime is short? H. And if we assume that the total number of short edges short edges in H, short edges in H is rho times the original sort of rho times the total number of edges in H, then the probability that xx prime is short approximately equal to rho. And so up to some constant, the probability that we can encode this mapping from x to u, essentially all these conditions are hold, is roughly equal to rho. So rho, again, is the fraction of short edges in the graph H. So let's denote by x this number of sort of this axis for which xx prime is short. The size of x is roughly equal to rho n. And so for vertices in x, we can record the mapping from x to x prime, then to u prime to u. For every vertex, we need roughly log eta n bits. Now, to store x itself, we need roughly, so the entropy of a random set of size rho n is approximately equal to the size of the set x times log 1 over rho. And so together we get to store that set x, a subset, right, of vertices in H, and the restriction of the mapping pi from those vertices to G, we need this number of bits. It's the size of x times log eta rho to the power of -1 over n. So again, eta was the size, sort of eta n was the size of the largest ball of radius 3 delta, and rho was the fraction of short edges in H. And but the entropy of this pair x and restriction of pi to x is approximately equal to the size of x times log n. Because for every vertex in x, there are n ways to pick a neighbor. So roughly it's x times log n. And it shows that eta should roughly be equal to rho. Again, I'm missing some constants here, but that's approximately correct. And this finishes sort of this sketch of the proof. Okay, so any questions about the proof? Maybe, yeah, okay. Yeah, so let me finish the talk. So to summarize, so we gave a new model for the balanced cut problem, and we also studied similar problems, similar models for the minimum feedback arc set problem, for the correlation clustering problem, and gave constant factor approximation, sometimes even 1 plus epsilon approximations. We actually implemented some of these algorithms. So we implemented an algorithm for the correlation clustering problem, and it works well on the synthetic data. An interesting question is whether this model is realistic, and it's not so easy question to answer. It's not so easy to say how to test this sort of hypothesis. Again, interesting direction is to say whether we can implement this algorithm or maybe a variant of this algorithm. As I said, we implemented a variant of this algorithm for the correlation clustering problem. Okay, and of course we can try to generalize this model in other directions and ask various questions about these models, whether we can get good approximations, whether we can recover pieces L and R, etc. So that's it. Thank you.
There was a lot of questions in the process, but probably now that the grand picture is clear, there are more questions.
How do you say that, like, the model approximates reality in a good way? Like, what are the methods to understand that?
That's a very good question. So I don't know. I mean, that's really, it's not so easy, right? So what is the meaningful way of doing it? One particular question, specific question, is to see whether sort of that structural result holds pretty much for real life instances, and that would be one direction. We don't know whether it holds in reality. It also probably this model is good maybe also for instances coming So it really depends, coming from one application, but maybe not other. For example, for maybe, I don't think that this model is good for computer vision, sort of for images. So graph partition problems are used in computer vision, but I don't think that this model would be realistic for various segmentation problems. But it might be more realistic for various problems with social networks. Yep.
My question is also related to application issues, and I invited my students here to listen to the talk just because we also studied similar models. We were attracted by the title Balanced Cut, and we use mainly spectral clustering techniques to this end. And maybe some comment how your method is related. Maybe we can use it or not for similar graph clustering tasks. So we need some feeling.
So first of all, of course, this work is rather theoretical. So if you care about practical implementations, I hope that's something to study, and probably you will need to tweak this algorithm a lot to make it work in practice. How it's comparable to spectral methods in practice, again, I don't know. If you think about this model, then an interesting question whether spectral methods work for this pi model. I don't know. I mean, we tried actually to see. Even we try to come up with a spectral algorithm for weaker models, and somehow our arguments break, so they don't work.
To me, your scheme when you use the adversarial was really interesting, just because you can use it, for example, to check whether your spectral clustering technique is stable or not on your data. So you can use it like noise, and fault-tolerant clusters should be checked whether it's possible or not with this algorithm. So I like it very much.
Thank you. Do you know whether this balance cut problem is in the heart also for approximation?
So yeah, it is APX hard. So yeah, you can get there is some epsilon, and you can get approximation 1 plus epsilon. Now, the interesting question, what kind of approximation you can get. So under some complexity assumptions, but very strong assumptions, honestly, you can get a constant approximation. So that assumption is it's tailored for graph partition problems. So it is not. No, it's much stronger than unique games. It's a variant of unique games with very strong variance. So because of course, one complexity assumption that this problem doesn't admit a constant factor approximation. Under that assumption, obviously, the problem doesn't admit a constant factor approximation. So that assumption is different, but it's very tailored for graph partition problems. So I think it might be true, but it's interesting to prove that complexity assumption to begin with here. So, yep.
Can you clarify, please, that on the third step of your algorithm, you said that we should remove a bit more heavier than 3 sigma ball, and we should decide artificially how much we should.
Right,
can you clarify, please, how we decide?
So there are kind of 2 ways of doing that. So you can just sort of go over all possible radii between 3 delta and 4 delta and just pick the best one. And of course, you need only to sort of, you can discretize, because you don't discretize sort of by distances to other vertices. Another way, maybe a better way, is you do the following. You take this ball of radius 3 delta, you kind of collapse it, and you collapse also sort of the complement of the ball of radius 4 delta. So you only have a graph, so you have source, that's the source is a ball of radius 3 delta, and sort of the sink is the complement of the ball of radius 4 delta, and then you just run the min cut algorithm, and that's what you do, and you find the cut that kind of cuts, that removes the ball of radius 3 delta and its kind of small neighborhood within a radius of delta. And it's easiest to show, it's very standard argument. I can show it maybe after the talk, that the cost is at most SDP over delta on the cut.
No more questions, so let's thank you.